Okay, so the first speaker is Sreenath Manikandan. He will talking about detecting single gravitons and proving their acoherence with continuous quantum sensing.
Thank you. My name is Sreenath K. Manikandan. I am a researcher in theoretical physics at Nordita, Stockholm, Sweden. And today's talk, I'm going to discuss a way to detect single gravitons and also probe their acoherence with continuous quantum sensing. What I will present is based on the two articles. The first one with Igor Pikowski, who is at both Stockholm University and Stevens Institute of Technology, and then Germain Tauber, who is at Stockholm University, and Thomas Beetle, who is at Stevens Institute of Technology. And then the second work is with Professor Frank Wilczek. I want to begin this story. Of course, there was a very nice program at ICTS last week organized by Abhishek and Rajesh on the celebrating the 100 years of quantum mechanics. And I would also want to begin my talk by reminding how people in the early 1900s inferred the existence of a photon. So there were two pivotal experiments. The first one was the blackbody radiation spectrum, and their experiments were so good that people could figure out how black bodies radiated, does the intensity or the rate of emission and so on depend on the temperature as well as frequencies. There were very good predictions using classical electromagnetism that worked very well at low frequencies. Similarly, this was by Rayleigh and Jeans. Similarly, there was a prediction by Wilhelm Wien, which worked at the high frequency regime, but a uniform formula that worked across all frequencies and temperature ranges was lacking. And Planck was the person who came up with a fit that worked across all frequency ranges. Furthermore, the genius of Planck was that he was also able to give an explanation that the walls of these black bodies are made of harmonic oscillators, which produce energy in discrete units proportional to their frequencies. And this proportionality constant is, of course, what we now call the Planck's constant. Einstein was also independently interested in this problem, and he was primarily motivated by Wilhelm Wien's formula and the frequency of and the behavior of high frequency light using statistical mechanics arguments for a box of high frequency light. He was able to say that light behaved as particles in at high frequencies. Furthermore, the genius of Einstein was that he was able to extend this argument to say that not only in existence, but also in interactions with matter, light behaved like particles. And this also explained, he gave an explanation to the photoelectric effect, the observation that when light bulbs shine on metal surfaces, photons induce emission of photoelectrons or electrons. And there were two key features of the photoelectric effect. One is that this is a resonance effect. So if you increase the intensity below resonance, you don't see any photoelectrons emitted. But if you increase the intensity above resonance, one can measure the stopping voltage to stop electrons from getting emitted. And that was independent of the intensity, essentially. So this led to the conclusion that it is essentially a single photon that does the job of kicking out a single electron. And then later, Philip Lenard and Millikan tested the photoelectric effect in experiments. Now, if we fast forward to today's quantum optics, we know a lot more about the quantum nature of light. One of the things is that, of course, there is a semi-classical limit of QED that also works to capture the essential features of the photoelectric effect. However, it is important to note that the semi-classical limit, since we know that electrodynamics is quantized, the semi-classical limit is a convenient approximation, and it comes with some issues such as the conservation of energy would be violated. In fact, this is something that had bothered Einstein too. In a letter to Jacob Loeb, his dear friend, in 1910, he says, "At present, I have high hopes for solving the radiation problem, and that without the light quanta. I am enormously curious how it will work out. One must renounce the energy principle in its present form." But within 1 year, at the 1911 Solvay meeting, Einstein says, one can choose between the quantum structure of radiation and the negation of an absolute validity of the energy conservation law. Who would have the courage to make a decision of this kind? We will agree that the energy principle should be retained. And furthermore, if you come to the 80s and so on, we have very interesting experiments, very helpful experiments from Rochester, including demonstration of Poissonian statistics and Hongo-Mandel effect and Wigner negativities, and also Bell inequality violation experiments are thought to be the only loophole-free test of non-classicality that further improve our understanding of the quantum nature of light or the existence of a photon. But it is important to remember that observing matter and light exchanging quantum of energy, that is photons, in discrete units was an important first step in formulating the quantum theory of light. So in this talk, we ask the following question: whether we can detect a graviton as an exchange of energy between matter and gravitational waves. For this, I want to start with what is the quantum mechanics of gravitational waves that we will be using. We are working in the linearized gravity low energy regime. In this, of course, there is discussions around what is the full quantum theory of gravity, but there is a good agreement that in the low energy regime, whatever the full quantum theory of gravity might be, it should be an effective field theory that has many qualitative features of electromagnetism, because it's a linearized effective field theory. And but there are subtle differences that are also important. So we will start with gravitational waves. Of course, we can get gravitational waves by linearizing. It's also prediction of the full theory, but we can linearize the Einstein's equations. And then GR has 10 degrees of freedom, but in the linearized theory, we can apply gauge conditions, because slowly varying diffeomorphisms are a symmetry of the theory. From 10, we'll be left with 2 degrees of freedom. These are the two polarizations of gravitational waves, the plus and cross polarizations. And then the quantization would be that we promote, so there is a classical wave equation that gives these plane wave solutions. And the quantization would be where we promote these Fourier amplitudes to operators. And so this is the transverse and traceless gauge, which is very useful representation for how gravitational waves are described. But then the interactions with matter are better described in a different gauge condition, choice. This is the local inertial frame or Fermi normal coordinates or proper detector frame. Essentially, by going from the TT gauge to the, it's transforming the gravitational waves in TT gauge to the local inertial frame, we'll get that the leading interaction between gravitational waves and matter is quadrupolar in nature. If you remember, in electromagnetism, light couples to the dipole moment of charge distributions, but gravity, there's only one sign of mass, and it couples to the couples at the quadrupolar order. Now the question is whether, so we now know what is the quantum description of gravitational waves and what is the interaction Hamiltonian between matter and gravitational waves. The question to ask is, can we detect individual gravitons? And this was a problem that people thought it would be impossible. For example, if you look at Weinberg's text on gravitation and cosmology, he estimates what is the rate that a hydrogen atom, initially prepared in an excited state, goes to the ground state by emitting a single graviton. And he gets a number which is 10 raised to minus 44 per second, which was actually corrected by Born and Rothman. There was only a numerical mistake in his calculations, so 10 raised to minus 40 seconds per second, which means that we will have to wait 10 raised to 40 seconds to see a graviton spontaneously emitted from a hydrogen atom. If you know the age of, if you recall, the age of the universe is approximately 10 raised to 18 seconds. So this means that we will have to wait much more than the age of the universe to see a graviton spontaneously emitted from a hydrogen atom. So needless to say, there is no chance of observing such a transition. And the way this calculation is done, of course, by using the quantized gravitational waves of the linearized theory. And we know the interaction Hamiltonian, we sandwich that between the initial and final states, appropriate states for the radiation field and matter, and we get a Fermi golden rule rate that is 10 raised to minus 40 second inverse. If you look at Born and Rothman's paper, you can find a very nice discussion about various gauge issues and the gauge invariance of the linearized approximation and so on. Similarly, Dyson was another person who wanted to see if one can detect single gravitons. Among other things, he looked at whether LIGO, which is our best classical detector, can detect individual gravitons. So LIGO essentially contains any gravitational wave that we measure at LIGO, the strain amplitudes, when we translate to a number of gravitons, we'll find that it contains approximately 10 raised to 36 gravitons. We get this number by dividing the energy density of gravitational waves with the energy density of a single graviton. So Dyson concluded that we have to improve our sensitivity by 36 orders of magnitude to be able to see a single graviton at LIGO, which is also seems very impossible. But then in a recent work, we showed that it is possible to detect individual gravitons. So first I would address how we overcome these challenges. The first thing is that we do not need single gravitons to arrive to observe single graviton signatures in experiments. Just as in the photoelectric effect, we can have light bulbs shining on metal surfaces that kick out individual electrons, and we have a means to conclude that it is one photon that did the job. And then LIGO, after all, need not be the best detector to detect individual gravitons, because LIGO measures position as the observable, and to see quantized energy exchanges, we should observe energy operator of the detector. And Weinberg was thinking in the right direction using atoms as detectors, but then the cross sections were very small. But what we do is that we consider massive acoustic, massive quantum systems essentially that would give collective enhancements from many atoms that would increase the chances of seeing the process. We also work in the LIGO band. There are two advantages. One, we can correlate with LIGO. And the second thing is that it also brings as many as 10 to 36 gravitons that we can work with. And then we will combine with continuous quantum sensing of energy of the bar detector that would allow us to infer single graviton exchange events. For this, we use Weber bars. So those of you who have not heard the name Weber, Weber was a pioneer in gravitational wave astrophysics. Around the time when people were debating whether gravitational waves truly exist or not because of this gauge invariance, Weber was the person who told, let's take a huge aluminum cylinder and see if it rings up when a gravitational wave passes by. But Weber was trying to detect classical gravitational waves, and they coupled very weakly with gravitational waves, the Weber bars. And it did not, although he made a few claims of detection of gravitational waves, there were not enough corroborating evidence. But we will show that this precise fact gives realistic, or the fact that they were bad detectors for weakly coupled bad detectors for classical gravitational waves gives realistic parameter regimes where absorbing single gravitons becomes a dominant effect. So we quantize the Weber bar detector. So there are many atoms. So if go in, each of these atoms will have an effect of the gravitational wave. But instead of looking at individual atoms, we look at collective modes of the bar detector, essentially solutions to the elastic acoustic wave equation. And these are acoustic modes, and they have well-defined frequencies. You can find them by applying the elastic boundary conditions, and then all of them have effective mass, which is m/2. So now we can translate the interaction Hamiltonian to add up the effect of, if we want to focus on one of the acoustic modes, we can change a basis essentially, and then we'll find that there is a leading contribution. Both these terms are quadrupole in nature. There is a length factor that comes out here. And there is a leading contribution which increases with the mass of the bar detector we use, as well as the length of the bar detector. And there is a subleading contribution, which is like the Weinberg-like effect on individual atoms. So now, first we can ask what is the new spontaneous emission rate? So for a niobium cylinder with typical parameter values, we find that there is a 7 orders of magnitude improvement in the spontaneous emission rate. This becomes crucial later, but this is still very small. But when we look at stimulator absorption rate, we find that for an aluminum cylinder of the type Weber was using, there is, and for a gravitational wave in the LIGO band, so the strain amplitude is something like 10 raised to minus 22, there is the chance of observing 1 graviton absorbed per second. So we use the first gravitational detection data to estimate this number here, which is again not surprising because these detectors were indeed proposed to detect classical gravitational waves. So we expect to have some response when a gravitational wave passes through. All this means is that when we convert this to the quantum description, we can find realistic parameter regimes where single graviton absorption can be significant. One can also solve the problem exactly. Gravitational waves have a time-dependent frequency, and this time-dependent problem can be solved, for instance, assuming the gravitational wave is in a coherent, quantum mechanical coherent state, using Lie algebra or other methods. And we find that the bar will get excited to a coherent state, where the coherent state amplitude can be written in terms of, if you want, in terms of the source parameters using stationary phase or other analytical methods, or even using the exact LIGO data. And we see that there is 36% chance of exciting a single phonon on the acoustic bars, acoustic modes, when the gravitational wave is stimulating the bar detector for typical, for any, that is a maximum probability of seeing an excitation. And we can also use this result to optimize what is the mass that we need to optimize the chances of absorption. We can just invert that formula to find a mass in terms of the source parameters which are included in chi if we want to look at specific sources. So here is, and the final ingredient we need is continuous quantum sensing of energy levels of the bar detector. And of course, I want to say that this various lectures at this program is a very good reference if you want to learn this technique. The idea is that we want to measure the number operator of an acoustic mode. So we couple that to a degree of freedom, potentially light. Again, this is, although I'm presenting a model, we do not know yet how to implement this in practice, but we hope that it is in principle possible and very realistic. So we use these Gaussian measurement operators that correspond to measuring the number operator of the acoustic mode, and we can time evolve quantum trajectories of this process. I also want to say that there are nice textbooks too, including Weisband and Milburn's book, and Andrew Jordan, who was my PhD supervisor, also wrote a recent nice book on the topic. And then, so here I show an example of simulating a single quantum absorption from a gravitational wave with a Weber bar detector. So these are the continuous readouts. And what I'm plotting here is the probability of various levels, the ground state and the first excited state. The pink window is a 4-second duration where we simulated a gravitational wave signal coming from a neutron star merger. And that blue vertical line corresponds to resetting our detector at a finite interval. So if we need to, here this continuous measurement is needed because the sources that we are looking at, like binary black hole mergers or binary neutron star mergers or neutron star black hole mergers, we don't really know when they are going to happen. So we will have to continuously measure, reset, measure for the coherence time, and then reset and keep doing this process. So here is a summary of how to detect single gravitons. We have gravitational waves coming. I think the latest update from LIGO is that you can see one gravitational wave per week or something like this. And then we continuously monitor the energy of the mode, one of the fundamental mode, let's say, of the acoustic bar resonator, and see if we see quantum jumps induced by gravitational waves. And to leading order, we can show that the absorption probability is proportional to a sinc function. So it's a resonance effect. And the probability also increases with the intensity of the radiation on resonance. And below resonance, you don't see a significant absorption happening. And this means that the more, if a more intense wave comes, more number of phonons will be excited. And classical LIGO can tell, of course, if there was a gravitational wave chirping through our resonance frequency. And we therefore call this a gravitophononic effect. And conservation of energy, which a semi-classical limit of QED or applied to gravity violates, suggests that a quantum of energy or a single graviton was exchanged between matter and gravitational waves. However, we would also say that this is not a proof of quantum theory of gravity. Seeing this would be an important milestone or first step in the same sense of the photoelectric effect, where one inferred the exchange of energy quanta between matter and electromagnetic radiation. So here are the requirements. For example, if we consider a gravitational wave in the LIGO band, the first one is a neutron star merger event. If we have a beryllium detector, we can of 15 kilogram. If we can ground state cool the fundamental acoustic mode of this system, we can maintain it at 1 millikelvin essentially to see the effect happening. And if you wonder where we are currently, there are these bar detectors of the type that Weber proposed, still in operation. They all are tuned to measure, in a way, the position degree of freedom of this acoustic mode, and they are looking at classical signals, including high frequency gravitational waves. However, we find that the kind of experiment we want to do, one need at least 2 orders of magnitude improvement in both the temperatures that we currently need, as well as the quality factors of the detectors that we would need. Now, I mentioned a few times this issue of taking the semi-classical approximation. And in the second part of this talk, I would like to address this question, whether we can discriminate different quantum mechanical states of the radiation field. Because, as you know, the semi-classical limit, or it's also known as optical equivalence by Sudarshan, it works generically for any linearized effective field theory that is quantized. The interesting thing is that we quantize the system by promoting the Fourier amplitudes to operators, and we can go back to the classical description by assuming that the field is in a coherent state, because the coherent states are eigenstates of the field amplitude operators. We can do this, and then we'll find that, and this is also because they are eigenstates. When we estimate the noise, essentially coherent states have 0 quantum mechanical noise or variance for these field amplitude operators, and such a procedure can be done. Therefore, to go beyond this limit, one has to see whether any signatures of quantum mechanical states different from coherent states are observable in our detectors. So we have a simple model for the interaction between the detector and the field. So this is a quite generic approach. We assume that there's a series of detectors coming and interacting with the field in the Markovian approximation. And in this a one parameter essentially. That parameter is the spontaneous emission. You can show that in this effective model that gamma naught is the spontaneous emission rate of the detector. And then we can approximate the time evolution Hamiltonian. And what is interesting is that when the field is in the coherent state and the detector is in the vacuum state, this is like a beam splitter interaction, and then the detector essentially gets excited to a coherent state as well. Now we can use the diagonal Sudarshan representation or Glauber Sudarshan P representation to estimate what happens to a generic quantum state of what is the effect of a generic quantum state of the radiation field on our detector. And using this diagonal form, we see that the detector gets excited in this way. And we can also estimate what is the probability that the nth level of the detector is excited, which has this particular form. And when you take, so now we know what are the probabilities that we would see in our detector. And we can also estimate the mean of this distribution for various quantum mechanical states that is encoded in this function P of alpha, and then also the variance as well. And we can also define a quantity that quantifies the statistics, which is Mendel's Q parameter as defined here. And if you look at this for a coherent state, what we find is that, of course, coherent states have a Poissonian distribution, and they also produce a Poissonian distribution on the detectors that we use to detect them. And the Mendel Q parameter is 0. For a thermal state, we find that the Mendel Q parameter is actually proportional to the intensity of the field, or the occupation number of the incident gravitational radiation or any radiation. And the noise can be quadratic. There is a quadratic term. The deviation from Poissonian statistics is quadratic in the occupation of the stimulating field. For a highly squeezed vacuum state, so one would need nonlinearities to produce these kind of states. What we find is that the noise is actually 2 times, the Mendel's Q parameter is 2 times what you would see for a thermal state, and the noise is also added, the additional added noise is also 2 times with a quadratic enhancement. And there are these class of states which are sub-Poissonian states for which the variance is smaller than mean. And for those states, the Mandel Q is between 0 and -1. So you do not get an enhancement that increases with the intensity of the radiation field. Full counting statistics can be done. We can do it now in quantum optics, but for cases like gravitational radiation where we have not even observed one click yet, it is good to see if there are simpler methods with just if we have the chance of seeing one more click, for example, 2 clicks at the detector, can we use that to infer any of such properties? And I'll show that it is indeed possible. As you know, coherent states satisfy a Poissonian distribution statistics, and detectors also show a Poissonian distribution. And it means that Poissonian statistics, they satisfy rigid relations between the probability of not observing a click or 0 clicks, and then 2 clicks, and then 1 click. In fact, 2 times P0 times P2 is P1 square. So, and this is satisfied by coherent states. And if I can make a ratio, which is 2P0, P2 divided by Pn square, and we get a number which is 1 for coherent states. Now I can also do this for a thermal state. I'll find that this ratio is equal to 2. It's an order of 1 difference. And then I can also do this for a highly squeezed vacuum state. I'll find that this ratio is equal to 3. Again, another order of 1 difference. For number states, we'll find that this ratio is 1 minus 1 over n. And in fact, one can show that to leading order, this ratio probes a second order coherence function for the optical field. So if it is, here Q essentially contains the Mandel Q parameter, and we are essentially looking for tests that like relevant in the gravitational context is when you have a huge classical radiation incident on our detector, huge number of photons or gravitons in the field incident on our detector, and we want to see if we can find deviations from a coherent state description for the field. And for a generic Gaussian state, we can also write down a formula for what this ratio might be. And we can use this as a test for acoherence or deviation from the statistics that is produced by a coherent state. Because if the gravitational wave is in a thermal state or a highly squeezed vacuum state, one expects that, for example, in the last stages of merger events, nonlinearities come into play. And therefore, there is no reasons to insist that the field is in a coherent state. These quadratic or higher order interactions can essentially make a highly occupied coherent state squeezed as well. So in principle, it seems that with the same detector, we can also tell whether the gravitational wave is in a coherent state or a thermal state or a highly squeezed vacuum state. Now, I also want to briefly show with a rough analysis what these numbers 1, 2, 3 and 3 means. They are essentially the values that you get for the second order coherence function, but they can also be understood in terms of the noise. For this, I use typical parameter values. So we estimated previously that the spontaneous emission rate for a typical detector is 10 raised to minus 33 hertz. And let's say there is a LIGO band gravitational wave, which I said has 10 raised to 36 gravitons. And then we have the measurement duration, which is approximately 1 millisecond. Then we see that the mean for a coherent state, this mean equal to variance, and that is approximately of order 1. But if I have a thermal state, then we find that the mean is of course of the order 1, because LIGO also do not see between to the leading order. But if you look at the noise, it is approximately order 2. And if we look at a highly squeezed vacuum state, we can use the same argument to show that it can be approximately of order 3. So what is interesting is that the same detector that we said could in principle detect graviton can also tell apart whether the gravitational wave is in a coherent state or a thermal state or a highly squeezed vacuum state. And since nonlinearities are expected to be significant at the late stages of merger events and so on, we expect that the gravitational waves that we would see might also contain these quantum mechanical signatures that can be probed in the experiment. So here are my conclusions. The first thing is, of course, that single gravitons can be detected, but we need macroscopic quantum resonators or quantum Weber bars, we also, so what we observe would be a stimulated single absorption of a graviton with such a detector. One would also need continuous quantum sensing of quantum gems, and the weak interaction helps because it, like I said, detectors, where Weber envisaged these detectors as detectors for classical gravitational waves, but it coupled essentially very weakly. So one could say they are bad detectors, were bad detectors essentially for classical gravitational waves. But this very fact that it's a weakly coupled detector can make it actually a good detector to see the quantum aspects of the radiation field. And of course, there are certain challenges that also needs to be addressed. For example, we need the continuous quantum measurements of the type that we discuss at this program at the macro level. So we are talking about continuously measuring a 15 kilogram massive quantum system, and we need to ground state cool these systems. So which means that is another challenge that potentially one could overcome with laser cooling or parametric feedback cooling kind of techniques. And then one also needs to, some of these issues can be overcome. For example, we can reduce the mass and so on if we were to go to very high frequencies, but we do not know of any good sources of gravitational waves at very high frequencies. Hence correlations with LIGO or other sources might actually help improve the requirements that we have. And of course, this is a quanta, this exchange of quanta is what we call the gravitophononic effect. It is analogous to the photoelectric. This would, if observed in an experiment, this would be similar to the photoelectric indication for the existence of photons. And what is furthermore interesting in this context is that with the lowest order click probability, if the detector starts to click, then what do we do next, right? So if we also have access to the probabilities of seeing at least one more click, in the sense that, so if we have a series of detectors, we can also do the statistics as a number of independent detectors, or the same detector, if it is harmonic, we go to higher levels of excitations in the harmonic detector. And we'll find that there are tests that are possible in the seemingly classical limit, which means very large number of quanta occupying the field. We can still tell apart if the gravitational wave is in a coherent state or a thermal state or a highly squeezed vacuum state. These classes of states are interesting because there is also a proposal earlier in 2021 by Parikh, Wilczek and Saharide, where they looked at whether the noise that you see in LIGO can be used to infer the noise of gravitons. And it turns out that they are the same class of states with this superpoisonian enhancement in the noise that could in principle be detected. And I want to conclude by showing this essay where we discuss briefly about how our proposal would relate to the earlier days of detecting quantum mechanics, as well as the inference of photons as an exchange of quantum between matter and light. With that, I would like to thank you all for listening to my talk, and also thank my collaborators once again. Thank you.
Thank you, Sreenath. Yes.
Yes, thank you. I have a couple of questions. You mentioned various possible Weber bars. But early in the talk, you said aluminum is much better than niobium. And just to understand that example, it was in that case on what basis?
So I did not. Sorry, niobium can also be a good detector. What I was comparing there is that one, I said what is the spontaneous emission rate for niobium, and that was small. But for it is also small for aluminum detectors.
And small because of what? Because of the difference of mass, or what parameter?
No, it is small for any. So if you look at any potential detector massive system, and you couple to gravity and estimate the spontaneous emission rate, it is typically a small number. Okay. And it is also true for the aluminum, because here it is what I am showing is the stimulated absorption rate. And stimulated absorption is basically spontaneous absorption, spontaneous emission rate times the number of quanta that is stimulating the system. And that 10 raised to 36 factors into getting this 1 hertz essentially.
Okay, let me just, one follow-up simple question.
Yeah, sure.
This is about your conclusion. You mentioned that you need ground state cooling of Weber bars. Would you care to state a temperature that would mean for those degrees of freedom?
Yeah, so ground state cooling, so once the system is ground state cooled, we can maintain it at 1 millikelvin. But we are talking about frequencies in between 100 hertz to 1000 hertz and so on. Right. So if we want to bulk cool the system, that would mean that we have to cool to something like nanokelvin. But we don't always have to bulk cool. We can do some other way of reaching the ground state with parametric feedback or laser or other techniques instead of bulk.
Okay, so I heard a lot of things, but I did hear nanokelvin, so 10 to the minus 9 Kelvin.
Yeah, okay. But that is if we were to bulk cool the system to the ambient. But if you do, there are other ways to essentially prepare quantum mechanical ground states where you don't use conventional cooling, right? You can,
But you can always discuss it in terms of the temperature that's achieved.
Yeah, exactly. Yeah.
Okay.
Okay, so it's
in case of collective absorption processes, for photons, the Mossbar effect is well known, and it has been observed by cooling the system to a sufficiently low level. So the kind of estimates which you need for improving the quantum sensing and things like that, have you worked out how it will affect the detection of the Mossbar effect? Because it is directly accessible, so you can compare how well things work.
Yeah, can you name once again what effect?
Mossbar effect, MOSSBAUER.
Mossbar. I'm not familiar with what that is.
Okay, it's absorption by a photon by the whole crystal instead of just one nucleus. That is how it is observed.
I see, but it is.
It's a very well procedure.
I see.
50 years old or something.
Yeah, so here it is effective, at least the sounds similar in the sense that these collective modes are essentially collective modes of the whole crystal, and we are quantizing that. And therefore, it almost sounds like we are also talking about a collective excitation by the whole thing behaving as if one quantum mechanical system. So yeah, so the degree of freedom that we quantize has many atoms, but it is a collective mode, and it goes. We hope that it will go from its ground state to an excited state, the first excited state, as one stimulus. So I think it is similar to the.
No, you should look up the.
I will do that. Yeah.
Strategy which is exploited by Mossbar effect.
Thank you. Yeah.
And if your analog things can be tied out on the photons, it will give you estimates of how well this thing can work.
Exactly. Yeah, we'll do that. Thanks. Sai has a question.
Sorry, I mean, you were actually right on the correct slide just a second ago. Yeah, so I had two questions essentially. David already asked the first one, which was about achieving this kind of motional ground state. I mean, I know from a little bit of work that I've done on mechanical ground states of nanomechanical resonators, that is already incredibly hard.
Yeah, again,
this is 15 kilos. I understand that at some point we're asking you the same question, Sreenath, but like, it almost beggars belief that you can get down to the motional ground state. Like, so you've done detailed numerics on this?
Basically, so I can give two comments. One is there are two interesting papers. One is from Caltech, where they tried to cool down the center of mass motion of the mirrors they are using. It's something like 10 kilogram, but close to n equal to 10 occupation. But the catch here is that it is the center of mass degree of freedom. They are not looking at the kind of acoustic modes that we are looking at. And there is another work which essentially, also to answer your question, I think this work summarizes various mass ranges and temperatures that are currently achieved in various systems. And on the left hand side, you'll see that it's all very very small masses, essentially, that where people have been able to cool down.
So Sreenath, in this context, I just want to ask, typically if you want to go down to the mechanical ground state, one of the questions is mechanical isolation, right? Because you can't have your table vibrating because it'll just repump the system.
Exactly, yeah.
So what kind of mechanical isolation are you thinking about to kind of maintain this ground state?
Yeah, so one thing is that we don't want to cool down the center of mass degree of freedom. We are cooling down, so the frequencies, for example, it's something like 100 hertz or between 100 to 1000 hertz. And these frequencies, hopefully there are not many noise sources at these frequencies other than an incident gravitational wave. And the other question, you also had a question about if I had done calculations on similar. So there is, for example, there is parametric feedback cooling, which is a well-known technique classically to start from very high temperatures and reach up to order of 1000 phonons or so, and then people will do linear feedback cooling. But then I have another paper with Sophia, who is also in this paper, I think. Yeah, so we had a paper where we showed that if you just use parametric feedback cooling, the absolute quantum limit of what you can achieve with phase control is that you can go to below 1 quantum. You can reach 0.83 occupation. That is below 1 quantum. And this is, of course, the question is, can we do that at 15 kilogram? And that is, of course, very challenging. One has to figure out.
And one last question. You had a POVM where you had a number operator in the exponent.
Yeah.
And could you just, please tell me how to implement that?
Yeah, so this is typical. It is typical in the sense that it is the standard measurement model. There's also an identity to the R. The way one would model this is by coupling the number operator. So we have an interaction Hamiltonian that couples n to, let's say, a quadrature of a field. And then we time evolve the system and the meter. And then we project on the conjugate of the, so if it is coupled, n is coupled to x, I measure p of radiation field that is coupled to the system. And do this time continuously, and then one can implement that. And this is how people measure sigma x or sigma z for qubits, and even x and p of harmonic oscillators. One could imagine a similar homodyne type of detection in the end that would implement this. Yeah.
Thank you.
Okay, so thank you very much. Let's thank the speaker again.